let's talk about chapter 19 here. Let's go ahead and get started. There we go. So we're going to be talking about electric potential and the electric field. Talking about potential difference is where we start, and then we move into talking about the electric potential in a uniform electric field. Then we'll talk about the electric potential due to just a point charge sitting there and how to calculate that. And then we'll discuss equipotential lines. And that's it. So starting with section 19.1 on batteries, for example, we can move it across states through power lines. We can see it jump from clouds as lightning. There's an important concept, though. Voltage is not the same as energy directly. For example, you could have a motorcycle battery and a car battery. They might have the same voltage rating, but a motorcycle battery would not be able to start a car because it doesn't have enough oomph, and we'll talk about that in a little bit here. But so let's say you are talking about a free positive charge, a Q, a charge, a little marble of positive charge. Let's say you accelerate it by an electric field. Because you know that F is equal to Q times the electric field. So what does that mean? That if you have a charge Q and you expose it to an electric field, it's going to feel a force this amount. And remember that F equals ma, so when you calculate that force, or when you experience a force, you get an acceleration. So if you put a charge in an electric field, it will accelerate and it will gain speed. So you will convert something into kinetic energy. And this process is exactly the same as dropping an object and watching it accelerate in a graph picture from the book here. So basically you have some positive charges here and some negative charges here, and that, remember, electric field lines begin on positive charges and end on negative charges. And when you have a line of charges like this, it creates a nice uniform electric field. So if you plopped a charge in there, the positive charge is going to be attracted to the negative side, and it's going to be pushed. It's going to accelerate. It's going to feel a force, and it's going to be accelerated that direction. So that's what that's showing, and it's the same as if you put a mass on a hill and let it go, and it rolled down the hill. You're going to convert gravitational potential energy into kinetic energy. In the same way, you can convert electric potential energy into kinetic energy, but instead of accelerating marbles down a hill, you're going to accelerate electrons, for example. So when a free positive charge is accelerated, it is given kinetic energy. This process is analogous to an object being accelerated by a gravitational field. Okay, so repeating that. The electrostatic or Coulomb force that does this is a conservative force, which means that the work done on the charge does not depend on the path it took. So this charge, you could have it go around like that. The only thing you care about is it changed this direction, is how far did it move in the electric field. Okay, not perpendicular to it, but parallel to it. So that's what a conservative force is. It's the same as gravity. In order to calculate gravitational potential energy, all you cared about was high up in the air something was, mgh. You didn't care about if it took the stairs, a spiral staircase to get to the top. All you cared about was the height that it changed. You calculate how much gravitational potential energy you gained by taking the force, mg, multiplying it by the distance that you traveled in that field. So you get force times distance. We call the analogous quantity electric potential analogous to gravitational potential energy. We call this just electric potential. So we can calculate the electric potential the same way we calculate gravitational potential energy. Take the electric field and multiply it by the distance, force times distance. Remember, the electric field is the force divided by a test charge, a Q. So this is almost the same as a force times distance, and technically it would be force per charge times distance, and that's going to be the electric field times distance. Okay, we just cancel out that one of those charges from Coulomb's law. So we end up getting this equation, which we know the electric field for a point charge is just kq over r squared. And if we want to calculate the electric potential surrounding a point charge, it's just the electric field times the distance you are away from the point charge, r. And you can see that if you do that, you get an R over R squared, and that's going to cancel out one of the R's. So you end up with KQ over R for calculating what the potential is around a point charge. You can do the same thing if you have the parallel plate capacitor and you want to know you're traveling from this point to that point. Your R is going to be the distance that you are from this wall, and how far are you there to calculate what the potential is inside. It's going to be a little bit different equation, and we'll talk about what that is. But the idea is you only care about how far in the field you've traveled from the charge to calculate the potential. So more generally, the voltage potential is defined as the potential energy divided by Q. So this is just like F over Q times distance. So force times distance is your potential energy, and the voltage would be the electric field times the distance over Q, or force times distance over Q, to get rid of one of the test charges. So that way the voltage is not dependent on the second charge you put in there to manipulate the field, but you might start with a test charge to create it. Okay, so this change in potential, if you go from the positive to some point else in there, that change is called the potential difference, just like changing heights in a altitude for calculating change in gravitational potential energy. The unit of this potential is called the volt, and it's a joule per coulomb. Okay, and that's joule and that's coulomb. Okay, so that's where that comes from. Now the electron volt is a new unit here we're going to talk about in a couple of seconds, but I just want to go over these examples they have in here. So suppose you have a 12-volt motorcycle battery that can push 5,000 coulombs of charge, and a 12-volt car battery, so they have the same voltage, but it can move 60,000 coulombs of charge. How much energy does each deliver? Okay, so they both have a potential difference of 12 volts, but the relationship is that the potential energy is equal to charge times the change in voltage. So the potential energy for the motorcycle versus the car, the difference is the amount of charge that it can move. So you can get 60,000 joules here, or 72,000 joules here, for comparing the motorcycle and the car. So that's your where that charge comes in when relating total potential energy to the voltage. So energy and potential are not exactly the same. You need to consider the charge there when you're doing that. And then you've got another question here. When you got a 12-volt battery running a single 30-watt headlight, how many electrons pass through it each second? So this is trying to get us to think about current, and we'll talk about that in the next section. So the first thing you have to do is calculate the charge. So we have 30 watts, which is joules per second, and we move it in 1 second. And then we have a 12-volt battery. So we can calculate the charge by saying we have negative 30 joules in a second and 12 volts, and that gives us 2.5 coulombs of charge. And then we know that there's 1.6 times 10 to the minus 19 coulombs for every electron. So you divide that out and you can calculate how many electrons there are flowing around that lamp in that problem. Okay, so now let's talk about the electron volt. So the electron volt is a unit that we use when we're trying to calculate very small things, okay, the energy of a fundamental unit. So at the nuclear level, sometimes we want to calculate what an electron is doing. We call the unit of energy, the smallest unit of energy, is called the electron volt. And it is simply if you took an electron and you accelerated it through 1 volt of potential difference, or you allowed 1 volt to accelerate an electron, how much energy is gained by the electron during that process. So if you have a parallel plate capacitor here with a nice uniform electric field, and you put an electron in there and you let it go and it accelerated through 1 volt, and the VA and VB, the difference here, VA minus VB, would be 1 volt. So if whatever this would be 0 volts and 1 volt, for example, as long as the potential difference is 1 volt, and you ask yourself, after this accelerates, and then right before it gets ejected out of there, you ask, what is the kinetic energy that it has? That's 1 electron volt, and it turns out to just be 1.6 times 10 to the minus 19 joules. Okay, so that's the nice thing. That's the fundamental quantity of energy that we use. It's a unit. That's all. Okay, so and you might hear tera electron volts or giga electron volts or mega electron volts or MeV or keV or TeV. Those are all just measures of electron volts. All right, so conservation of energy. In any case, you always have the kinetic and the potential adding together to be a constant. So you can take potential energy from the battery, use it to accelerate an electron and give it kinetic energy, and then you can have that hit something and do stuff. So this is the same as in section 151 or the earlier chapters. We did conservation of energy for, you had a ball up in the air that had a mgh amount of energy, you dropped it, and right before it hit the ground, it had 1/2 mv squared amount of kinetic energy, and you transferred the energy from one source to another. Same thing happens here. You can do the same idea, and the example that they show here is you want to calculate the final speed of an electron after it's accelerated from rest through a 100-volt difference. Okay, well, we know that the potential energy of the electron is going to be Q times V. So we're going to take the charge of the electron, we're going to multiply it by 100 volts, and that's going to be the potential energy it has. And then we're going to convert all of that potential energy into kinetic energy, which is 1/2 mv squared. So we're going to need to know the mass of the electron and the charge of an electron to do this. And if we just solve for v here, we can get that the velocity is going to be the square root of 2 qv over m. Plug in those things, the mass of an electron down here, and the fundamental charge on an electron there, and we get that it goes at about 5 million meters per second. Okay, so that's pretty fast to accelerate an electron out of a 100-volt potential difference. Okay, so that's the type of problem you're going to be doing, is calculating the velocity of an electron after it's accelerated through a certain potential. That's a very common thing, so be able to do this equation and set that equation up. Okay, and again, how do you do it? You start with your total kinetic energy, potential energy initial, set it equal to your total kinetic energy, potential energy final, and in this case, there's no initial kinetic energy and there's no final potential energy, so you start with all of your potential energy and turn it all into kinetic energy. Okay, so that's that. Okay, moving on to section 19.2. A uniform electric field is produced by placing potential difference across two parallel metal plates. We call that a capacitor, or parallel plates if it's really big. We can use either the change in voltage, the potential difference between the plates, or we can talk about the electric field that it generates. Both of them are fine. The change in voltage is more related to energy, and that's a scalar. It doesn't have a direction, whereas the electric field is more related to force, and it's a vector. So depending on what you're trying to do or accomplish, you're going to want to consider one or the other in your problem. But the work done by the electric field to move a charge Q from a positive plate to a negative plate is minus Q times delta V. So if you want to take this charge, it's a positive Q, and you want to move it from the positive side to the negative charge, to the negative side, the amount of work you're going to do is minus force times distance, and the result of that is minus Q times the change in potential. The relationship between V and E for parallel conducting plates, and this is the magnitude of V and the magnitude of E, is this, and this is only for a parallel plate capacitor. This is only for the electric field when it's uniform. So if I give you this geometry, and this is not a point charge, this is a line charge, the two line charges, two parallel plates. The electric field inside here is constant no matter where you are, doesn't matter where you go in there, okay? If you're here, if you're there, if you're here, if you're here, if you're here, the electric field is constant, it's uniform, that's why we do it. What is it? It's just the voltage between A and B, the total potential difference, divided by how far apart they are. That's it. So what's the gap here? D. And what's the potential difference? So if it was 100 volts and it was 5 centimeters apart, then you do 100 volts divided by 0.05 meters. and there's your electric field. That's it. And you can bring the D up there and get that the voltage then is just the electric field strength times the separation. So that's another equation you're going to have to use all the time. I'll give you a couple parallel plates. I'll say the voltage is on it is this. What's the electric field strength if it's separated by that far? So you'll want to calculate the electric field if I give you those two numbers, or I could give you the electric field and this number and ask you what the potential is, vice versa. Okay, the units here for electric field is a Newton per Coulomb. Remember, it's force over Q is electric field definition. Coulomb is equal to or equivalent to 1 volt per meter. So those are your two units to know what a meter is. Then V over D automatically comes out of that equation, and a Newton over a Coulomb, you know that's a force, and Coulomb is a charge, so there's your F over Q, and that potential here, lower potential there, so your arrows point from the plus to the minus, and that's how that works. And we've got an example here. So this what's the highest voltage between two plates? So we know here that the breakdown happens after about 3 × 10⁶ volts per meter for an electric field. So that's sort of your maximum electric field strength. What's the maximum voltage then if your plates are separated by 2.5 centimeters? So our electric field is 3 million volts per meter, and our separation is 2.5 centimeters. And we just plug that in, and we get that the maximum voltage is 75,000 volts. And that's about a lightning bolt. Well, they're about 1 million volts, but if you get 75,000 volts in like a Tesla coil, maybe you've seen these things. If you haven't, Google that, Tesla coil, and you'll see these little sparks shooting off. So you get about 75,000 volts, and then you'll get little gaps like that to happen. As you go higher and higher and higher, the lightning bolts will be able to reach further and further and further because it's ionizing the air basically. Okay, so so, you know, that's how much voltage you have to, you know, if you're 2.5 centimeters, that's the potential difference for you to see a, what's that called? Static electricity. Okay, that's a spark chamber. Whoa, oh dear, I just did something bad. Okay, not too bad. Whew, that was close. All right, moving on. We are almost there. Okay, 19.3. So now let's look at a point charge. So this is going to be your most important thing to study because we're going to use point charges all the time. So point charges, like an electron, are among the fundamental building blocks of matter, but also if you have a large uniformly charged sphere, like a metal ball, it behaves like a point charge in terms of its electric field. So it is useful to study then the electric potential created by a point charge. There's your potential equation is kq over r. The electric field is defined as kq over r squared. So you see this is a vector and this is a scalar. Okay, and how do you get voltage again? How do you get this from that? You multiply by distance r, and that gets rid of the r squared. So this is electric field times distance basically, and that's kq over r for a point charge. So if you want to calculate you've got a point charge somewhere and you want to go a distance r away from it, what's the potential there? That equation will tell you at that point what the value of the potential is, and then same thing, this value at that point, if you use this equation, will tell you the strength of the electric field, and then the important thing is that the electric field will be pointing in that direction, so it will have a vector associated with it. And I don't think there's much more to that than that. Yeah, so then moving on to the equipotential line. So take these two equations, and we're going to talk about them when we do our equipotential line. So for a point charge, we can represent, for any charge, but we'll start with a point charge, we can represent electric potentials or voltages pictorially. The electric potential at some radius r has some value, right? And you can calculate what that value is using this equation or that equation to get the value of the electric field or the value of the potential. The electric field has a value at that same radius, but it also has a direction, and that's what makes it a vector. the electric potential is then uniform at a constant radius, constant value, whereas the magnitude of the electric field is constant on a constant radius, but the electric field is always pointing in a different directions. So the electric field is not the same quantity everywhere around, because the quantity includes direction. So that's a key difference between a vector and a scalar. So what does this mean? That means that if I go to there's my point charge, if I move a distance r to that point, the value of the potential is the same at that same r, and the value of the electric field is the same at that point r. The difference is, even though V is the same, and even though the magnitude of E is the same, E is here, E is there, now it's pointing there, now it's pointing. So you see how important it is, because electric field has direction associated with it. You got to make sure that you don't ignore that you would draw an electric field as having an amount, even though the total is the same. You're going to have some amount EX in the X direction plus some amount in the Y direction. And if our electric field is pointed all the way in one direction, then yeah, let me do this, clear all. Okay, let's go to a bigger, so let's look at this electric field. That's a vector, okay? That means it has a X component and it has a Y component. Okay, the key thing is that this is EX squared plus EY squared square root. That's the length of E, okay? And maybe I should make it in red so you know that it's that one. What about this electric field vector here? What about that one? Okay, well, it's got EX and EY, EX and EY. Does everybody see that this EX is different from that EX, and this EY is different from that EY? So the components are different, even though the square root of these components, EX squared plus EY squared square root, this and that are exactly the same, because that line is the same length as that line, but they have different components because they're pointing in different directions. So that's why the electric field changes. Even though the magnitude stays the same, its direction is different, so the components are different. Whereas the potential is constant all the way around and doesn't change because it doesn't have a direction associated with it. So those green lines, these are called equipotential lines because the potential is constant. It's equal along those circles, those points. So it tells you where the potential is the same. And if you trace around one of those circles, you don't do any work. It's like walking around a mountain without going up or down. You don't change potential energy, gravitational potential energy, so you don't gain or lose any gravitational potential energy. In the same way here, if you walk around in that circle, you don't gain or lose any potential electric potential energy. Okay, these green lines are called equipotential lines because the potential is constant as you move at a constant radius. Notice that the electric field lines are always perpendicular to the equipotential lines. That's the key here. If I go back here, there's my electric field line and there's my equipotential line, and the key is that there's always a 90-degree angle where the electric field line crosses an equipotential line. So that's one of your key takeaways, okay? Yeah, electric field lines are always perpendicular to equipotential lines, and you'll do a lab like that. Okay, so now you can see the equipotential lines get a little squished when you put a plus and minus charge together. They're not uniformly circles at constant radius. This gets a little more complicated because we have a little bit more math, and you don't have to calculate any of this stuff, but this is just showing you that how the equipotential lines and the electric field lines can help you understand what's going on and how a picture can communicate it a little bit easier than trying to do all the math. Okay, and then this is if they are the same charge, minus minus, you're going to have, this might be 10 volts there, 10 volts here, and then you can see there's a nice equipotential that wraps around both of them and then wraps around both of them on the outside, and those are the same potential difference. So that just means if you pushed a charge along here, its potential energy would not change because it's not going up or down in potential energy. Okay, inside of a, so these are just examples of different configurations. Inside of a parallel plate capacitor, then you have, or a parallel plate electric field, nice uniform electric field. So the electric field lines are nice and uniform, and then the equipotential lines are perpendicular to them and up and down. Okay, so if you got 100 volts of potential there, 0 volts here, it'll step down like going down a hill. It'll go down to 75 volts, 50 volts, 25 volts, linearly, nice and uniform from one side to the other. Okay, so that's how that works. All right, go over to here, and we've got an example. No, we don't have an example. And let's see if I had, oh, I thought I had another example there. Yeah, so this is the relationship. Okay, so yes, okay, so for a between two plates, like this last picture over here on the keynote, if you want to calculate what the voltage is at any one of those points, the voltage is just going to be the electric field strength times the distance. So since the electric field strength is constant in our graph here, the nice thing about this, the electric field, no matter where you are in there, the electric field is the same. So if you want to know what the potential is at some point, like that point, what you care about is how far from the edge are you, and we call that D. And so the voltage at that point right here is going to be equal to the electric field strength, which is constant throughout, times how far you are from the edge. And then that's how you get 75 after traveling a certain amount of distance. So you're going to have to do that, calculate the strength of the potential at some distance from a parallel plate. So you'll have to know that equation. Okay, otherwise that's all you have to do. So see you guys later.